Now let's do an example of a single stub matching network with a parallel open circuit. So we're going to begin with our ZL, which is 100 plus J100, just as we did before. The ZL point is the same. But if we want to do a parallel stub, the very first thing that we do is convert ZL to YL. So I did that by translating through the center of the Smith chart to the point YL. Now everything that I'm going to do is going to be very similar to what it was before. I'm going to rotate a distance d towards the generator to match the real part. So here's my distance d, and what I want to do is rotate towards the generator until I get to a point A, where I'm going to have YA, and I want YA to equal 1 plus JX, and I don't care what the X value is. So let's do that. We're going to rotate again towards the generator like this until we get to the real circle. And what I'm going to do is take my piece of paper, put it centered at the origin, and match up on the real circle like this. Right there is my point YA. That is where the real part is 1 and the imaginary part in this case is about 1.6, and it's positive. So right there, that's the distance d that I need to rotate. So let's figure out what d is. I'm going to draw a line from the center through the point of interest out here, and I need to define my distance d. So let's read what this is. Right there it looks like it's 0.46. Right here it looks like it's about 0.178, and I'm going to break that up in two parts as I just showed you. So my d is going to be this point, which is 0.5 minus 0.46. That's this little distance right here. And now I'm going to add in this distance, which is 0.178. So that's my distance d, and I have matched the real part of my admittance. Now what I'm going to do is add a parallel stub that is open circuited at the end. That's like the ones that I showed you in the picture at the beginning of all of these lectures. And what I want is I want my YS to be the negative of JX. So I want YS to be minus JX. Well, let's read what X is. It is 1 plus J, read this value, 1.6. So I want YS to be minus J, 1.6. Now let's move to our blue color and design our stub. So let's plot it out here. Here is 1.6 right there. This is YS. That is the input at the beginning of the stub. That's the value looking into the stub. Now let's plot the load of the stub. The load of the stub is an open circuit, but it is an admittance open circuit because we're working in an admittance chart. If this had been ZOC, if I wanted to find YOC, I would just translate it through the center of the Smith chart. Right here is YOC. This side would have Y for a short circuit, but we're interested in an open circuit in this case. So I'm right here at YA. I've defined my YS, and now I need to define my distance L, which is moving towards the load. So starting at YS, moving towards the load to my open circuit. So towards the load is this way. Very tempting to go that way, but that would be a mistake. Let's go towards the load like so. To get to my YOC, and that distance is L. So L is going to be equal to 0.5 minus, and let's read this value out here, 0.14. So it's about 0.36 wavelengths. Now, did you notice that I used the wavelength towards the generator plot? The wavelengths toward the generator line, that's this line right in here. If I had used the wavelengths toward the load line, if I'd used the wavelengths toward the generator line, it would have been wrong.